Section 11.1b is more with square roots. This time we're going to use something called the quotient property. But before we get there, I want to talk about when a square root or when a radical expression is in simplest form. There are three things. First, no radicand has a perfect square factor other than 1. And we dealt with that in the first video. When you have a square root and there's something under here that is a number, it cannot have a perfect square factor. And we learned how to do that in the first video. Number two, though, no radicand contains a fraction, so you cannot have something like this that has a number under a square root that's a fraction. And kind of like that is you can't have the denominator of a fraction with a square root either. Either of these two situations is not acceptable, and we must learn how to simplify. Now, you can eliminate radicals from the denominator by doing something called rationalizing the denominator. And in the next slide, we have a couple examples of how we're going to rationalize the denominator. So here's the quotient property I was talking about. It simply says that when you have a square root with a fraction, you can break that up into the numerator with a square root and the denominator with a square root. So let's use that. Here, square root of 10 over 3 can be rewritten as the square root of 10 over the square root of 3. Now, why is that important? Because we said you can't have a square root in the denominator, so I don't see how this helps me. Well, what it does allow me to do is it allows me to multiply this fraction by something that will eliminate the square root in the denominator. What can I multiply the square root of 3 by to get rid of the square root? Well, let's go down here a little bit and talk about that. The square root of 3, if I multiply it by itself, won't that give me the square root of 3 squared? And don't squares and square roots cancel, just leaving me a 3? So my idea here is I'm going to multiply by the square root of 3. I'm going to multiply by the same exact value that's already down there. Now I have to multiply by the number 1, so it has to be square root of 3 over square root of 3. So let's see what that does. Root 10 times root 3 is the square root of 30. And as we said down here in the blue, root 3 times root 3 simplifies to just be a 3. Now, there's no perfect square in 30. I have no square root in the denominator, and I have no square root over an entire fraction. So this is now simplified according to the three rules. I'll come over here to this one, root 12 over root 5. I cannot have that square root in the bottom, so I've got to think of what I'm going to multiply by to get rid of the square root of 5. Well, hopefully you've learned from over here, you multiply by the same exact square root. And we have to do the bottom and the top. So here we end up with the square root of 60. 12 times 5 is 60. Over square root of 5 times the square root of 5 is really the square root of 5 squared, which simplifies to just be a 5. Now, is there a perfect square in 60? The answer is yes. So we have to continue to simplify a little bit further. Root 60 is really root 4 times root 15. And we know that 4 is a perfect square, so the square root of 4 will be a 2. So this is 2 root 15 over 5. And that's my final answer. A couple things to note. If the 2 and the 5 shared a common factor, I could cancel them, but they don't. You cannot cancel the 15 and the 5, because this is the square root of 15. It's not a real 15, and this is the number 5. Same reason over here why I could not have canceled the 3 with the square root of 30. Because this is not a 30, it's a square root of 30. Here's some more work with the quotient property. Root 7x over root 8. I have to get rid of the square root of 8, so I'm going to multiply it by itself. Square root of 8 over square root of 8. So on top, I'll have the square root of 56x over square root of 8 times the square root of 8. Is just an 8, because when you square a square root, it wipes it out. Now we have to figure out, does 56 have a perfect square? And it does. Square root of 4 times the square root of 14. Now don't forget that x is still there. Over 8. And what is the square root of 4? Well, it's just 2. Square root of 14x over 8. Now in the last slide, I told you that if these numbers have something in common, you can cancel them. And 2 goes into 2 once, and into 8 4 times. So this will simplify even further as the square root of 14x over 4. Again, though, I cannot cancel this square root of 14 because it's not really a 14. It's a square root of 14, and I cannot cancel with that 4. Next example here looks like this: square root of 11y on the top, square root of 27. Now this one I'm going to handle a little bit differently just to show you there's a slight difference that I could make. I already know that the square root of 29 is made up of square root of 9 times the square root of 3. And the square root of 9 is a perfect square. So this becomes 3 root 3. Now if you go back to the original one, I could have pulled off 4 out of here. I could have pulled the square root of 4 out of there, and I didn't. Just I'm trying to contrast the two different ways to do this. So here I simplified the denominator a little bit, and now the number that I'm going to multiply by, I'll do that in green, is smaller than square root of 27, which is what I would have multiplied by. So it might make the multiplication a little easier. Multiply the tops, and we're going to get square root of 33y over 3 times root 3 times root 3 is 3. So this will just become a 9. So root 33y over 9. There's no perfect squares in 33. I can't cancel it, so I'm done. Here are some more examples. You may want to pause the video, try them on your own, and then I'm going to show the answers in a minute. So here's the work. Root 6 times root 6 is just a 6. Root 2 times root 6 is root 12. I pulled a 4 out, a perfect square of 4, and made the square root of 4 a 2. Cancel the 2 and the 6, so root 3 over 3. Here root 8 times 3 is root 24. Root 8 times root 8 is 8. Pulled out a 4, root 4 times root 6, which became a 2 root 6, and then canceled. If you recall back in chapter 8, we learned about two binomials that look like this, that have the same values with different signs. And if you remember, that created something called a difference of squares. You square the first term, you square the last term, and you put a minus sign in the middle. That idea remains true even with radical signs. Notice the 3 and the root 2 is the same. One's a plus, one's a minus. So when you multiply those, all you have to do is square the first term, 3 squared, which is 9. Square the last term, root 2 squared, which is just a 2. Put a minus sign in the middle, and in this case, 9 minus 2 is 7. That idea, binomials that look like that, are called conjugates. So I'll list a couple conjugates here. 4 minus the square root of 5 and 4 plus the square root of 5. Those are conjugates. How about 3 root 2 plus 9 and 3 root 2 minus 9? Those are conjugates. So hopefully you get the idea of what a conjugate looks like. Here are some more fractions we have to simplify, and we're going to use the conjugate idea that I just showed you. But before I do that, I want to show you why using the method that we learned before that won't work. Some people look at this and they want to multiply by root 3 over root 3 because they think that square root of 3 times square root of 3 will be 3. And they're right. But what they forget is they forget to take this root 3 and distribute. So what you would actually get is 6 root 3 minus 3 if you did that. So really, by multiplying by the square root of the number that you have here, you don't end up getting rid of it. So that's not going to work here, which is why we have to come up with this conjugate idea. So here, what is the conjugate of 6 minus root 3? Well, it's 6 plus root 3. So we're going to multiply by that. So on the top, we have a 2 times 6 plus root 3, and we're going to deal with that in a second. But on the bottom, whenever you have conjugates, all you do is take the first number and square it, the last number, square it, and put a minus sign. So let's continue to simplify that. 6 squared is 36, and root 3 squared, those will cancel, equals a 3. So we end up with 2 times 6 plus root 3 over 33. Now the reason I left this 2 out in front here is because the 2 might have canceled with the 33, and I wanted to make sure that it didn't. Now you actually could leave your answer just like that. The other way that you could write the answer, and the way that you might see the back of the book do it, is to distribute this 2 and get a 12 plus 2 root 3 over 33. That's also an acceptable answer and one that you should be aware of. So our second example is like the first. So what's the conjugate of 5 minus root 2? Well, it's 5 plus root 2. Again, I like to leave the 3 on the outside to see maybe if it will cancel later. On the bottom, conjugates take the first term and square it, the last term squared, and a minus sign. 5 squared is 25. Square root of 2 squared is 2. 25 minus 2 is 23. So this is a fine answer here, or if you prefer to distribute the 3, you can get 15 plus 3 root 2 all over 23.